So now this is chapter 4. We are going to talk about wallets. Wallets is software that users use to send and receive Bitcoin. And as it says here, it only affects users. It doesn't affect the spreadsheet or Lisa's work at all. So this is just for the users to be able to conveniently interact with the system. So typical duties of a wallet is to create new addresses and manage the corresponding private keys and transfer payment details from between wallets. So if I want to receive money from John, my wallet should be able to display my address to John in a good way. And I, of course, need to be able to make payments. So it should be able to create these messages to Lisa and also keep track of my funds so I can see my total balance. And also very, very important, backup private keys. So we will talk mostly about how to create new addresses and backup today here. We'll skim through the rest, but the most important parts here are how new addresses are created and how to back up private keys. So this would be a typical overview of this how wallet works. As I said, if John wants to pay for a cookie in the cafe needs to show. The cafe's wallet needs to show the address to John so that John can, for example, scan a QR code that includes the payment details. And this QR code here could say something like that, like something like this: CT:\address ? Amount equals 10. So this is a payment URI, and it works the same in Bitcoin, but in Bitcoin, it says Bitcoin : instead. So this is a payment URI, which is pretty standard in Bitcoin. So everybody will be able to scan such a URI. So John's wallet will scan these payment details and display them to John. Hey, do you want to pay 10 cookie tokens to this address? And then John clicks OK and the wallet will then create a message and send it to Lisa. So we will have a look at this third step here. How does the wallet create this message now? As I said that before, the wallets, one of the purposes of the wallet is to keep track of the user's funds. So this is John's wallet. He currently has 3 key pairs. And on the first key, he has 80 cookie tokens. On the second key, he has 30 cookie tokens. And on the third key, there's no cookie tokens at all. So his balance is 110 cookie tokens. So he should be able to afford a cookie for 10 cookie tokens. So when John hits the OK button, yes, I want to send 10 cookie tokens, then it's the wallet's duty to select a key pair to send the money from. As in this case here, the wallet will choose this key with 30 cookie tokens in it, and then create, sign, and send an email to Lisa. And when this message is sent to Lisa, both the cafe and the wallet, both the cafe and John's wallet will simultaneously watch the spreadsheet for changes. John's wallet will watch the spreadsheet for public key hashes that he himself owns. So he knows what to look for in this spreadsheet. And the cafe will do the same. The cafe will also watch the spreadsheet for public key hashes that belong to the cafe. And suppose now that John's transaction to the cafe is confirmed. It shows up here in the spreadsheet. Then both wallets will be able to notify their respective users. So John's wallet will say that, hey, your payment of 10 cookie tokens confirmed, and your new balance is 100 cookie tokens. And the cafe's wallet will be able to say that, hey, you just received 10 cookie tokens, and your new balance is 2,420 cookie tokens. Okay. And we are now going to talk about backup. This is a pretty hairy section, and it will lead us to talk about something called hierarchical deterministic wallets. But we'll take it one step at a time. So suppose that you want to back up. Suppose that John here wants to back up his wallet. He has this these 3 key pairs that he keeps in his wallet, and he wants to back them up. So he could do it like this, for example. This is one way to do it. The wallet could have a user interface that asks for an email address and a password, so that the wallet will take the private keys, put them in a file, and encrypt it with some password here. So the file will be encrypted and stored in an email inbox somewhere that John controls, or he can store it on his hard drive, or on a USB stick or something like that. But there are problems with this. This is a pretty naive approach. First of all, because password encrypted backups could be problematic, because those passwords might not be as good as you expect. And yeah, and also there are actually 4 problems with this. So one problem is that instead of just the backup, you need to keep track of both the backup and the passwords. So it's more stuff to keep track of. And also, it's really hard to remember a good password. And the better the password, generally, the harder it is to remember. And also, technology advances. A password that was good 20 years ago probably isn't very good today, because now stronger computers can have better chances of cracking the password. So as time goes, you probably need to improve your password security, because technology improves. And then it's really, really hard to come up with randomness yourself. Coming up with random data is really hard. But there's also a bigger problem. And this doesn't have to do with password encrypted backups. It could be plain text backups as well. So you are encouraged, okay, I'll start from the other end. When you create a new address in your wallet, you would have to make a new backup. Every time you create a new address, you would probably have to create a new backup so that that address is backed up too. And this is very, very tedious work to keep making these backups for each new address you create. And that, in combination with the second bullet here, that it's recommended to use unique addresses for each payment for privacy reasons. So every time you request money from someone, you should use a unique address, which means that every time you request money from someone, you also need to make a backup of your private keys. And this is not good. It's really tedious to keep doing this. Of course, you could do it automatically in some ways, but it causes a lot of headache, to say the least. So that's why I shouldn't say we, but people invented something called hierarchical deterministic wallets, HD wallets. And the idea here is that instead of just a bag of independent keys, you have a tree of keys that can be deterministically derived from a master key. So you have a master key and you can derive any number of children to this master key. And each time you derive the children, you will get the same set of children. So for example, this key here, each time you derive this key at index 1, you will get the same private key. So it's deterministic. I will go deeper into this, but what you can do using this scheme is that you can also organize your keys into different purposes. So this wallet, for example, has 8 keys, and they are organized into a shopping account and a savings account, if you will. We can call it accounts. So when you go shopping, you use these keys, and when you save, you use these keys. And you can have as many accounts as you like. So how do we then create this structure here? And then I will get back to how we do backups. You probably might be guessing that right now, but we'll get back to that. So this is how you would generate this tree. You would start with a random number generator up here. And this random number generator would produce a seed. For example, 128 bits of entropy, or 256 bits, or 512 bits, but a random seed. And from this seed, you will derive something called an extended master extended private key. And this is the key that you saw in the previous slide, master extended private key. This is the master extended private key. So I denote them differently here because it's not just a key, it's a key combined with something called a chain code. I will show you that later. But for now, it's just regarded as a key. And from this private key, you can derive children of this master extended private key. As many levels as you want, and virtually how many children under each key as you want. And we denote the master with M, like this. And each key has its own unique path. For example, this one here is M10, which means that it's starting from master, index 1, which is this key, and then index 0, which is this key. And this one on top here is called master extended private key, and all the children and subchildren are called just extended private keys. And these ones are called key path. Okay. So we will look more closely at these boxes here. We will start with the we will go back to backup now a little bit. So what is needed here to back up this full tree? Yeah, so it's the seed. If you have the seed, you can generate any number of keys underneath it. So you can, from the seed, recreate the full tree of keys. And this is really powerful because now you can, once you create your wallet, you can generate this seed, write it on a piece of paper, and put it in a safe place and sleep well at night. Because you know that no matter how many keys you create in your wallet, you can always be able to recreate them using the backup. So you only have to back up once. And this is really powerful. So let's look at this extended private key, or XPRV, as I usually write them. So this symbol here, a private key with a little pile of papers, that's an extended private key, and it consists of a private key and a chain code. And this chain code is used when you want to derive subkeys. And from this private key, you can, of course, derive the public key. So let's have a look at the first step. You have the overall picture up to your right. So now we are going to derive the master extended private key from the seed. Okay, so now we are going to derive the master extended private key from the seed, like this. So to your left here, you have the seed, and to your very right, you have the master extended private key. Let's see what happens in between here. So the first thing you do is that you hash the seed using something called HMAC SHA-512. This is basically like a normal hash function, cryptographic hash function, but it also takes something called a key. So it takes an input like this, which is the seed, and then it takes a key. In this case, it's just a hard-coded value called CT seed. In Bitcoin, it's Bitcoin seed. And the output is a 512-bit number. So I won't go into detail what this is. You can just view this as you hash this seed and this key here together and get an output. So the left 256 bits of this 512-bit output, the 512-bit output is split in half, and the left 256 bits become your new child private key, or your new master private key. And the right 256 bits become your chain code. So, and these two together will form your master extended private key. And of course, you can derive the public key from the private key, which is then your master public key. That's important for a later discussion. But right now we have created our master extended private key. And then we come to the next step. From the master extended private key, we want to generate the child keys. So as you can see here up on your right, we derive a sub key at a specific path. And as input, we have the master extended private key and an index. So we want to derive index 1 from this master extended private key and get M1. So again, we will start on our left here, which is our parent extended private key. And this is the same algorithm that is used for all child derivations, not just from the master. So this can be the master extended private key, or it can be any child extended private key in the tree. And then, so this is the parent extended private key. And here you have the child extended private key, which we are going to generate right now. Okay, so the private extended private key, the parent extended private key is composed of a private key and a chain code. And from this private key, we generate the public key. And then we use the public key and the index as input to this SHA-250, HMAC SHA-512. And as key, we will use the chain code like this. And as before, you can just view this as you hash all these things together. Like you hash these things together, and out comes a 512-bit number, just as before. And just as before, the right 256 bits is called the child chain code. This is the chain code of the child. And the left 256 bits can be viewed as a private key and added to the parent private key. So you take the parent private key and you add to it these 256 left bits. And you add it, of course, you add it with modulo 2 to the power of 256, because you want 256 bits keys. And the result of this addition is the new child private key. And these two together form the child extended private key. So this addition, we will come back to this addition later, but yeah, so it's important here that we add the child, the left 256 bit to the parent private key to get the child private key. And to be honest, I still think I've been working with this, and I still think this is hard to wrap my head around. So don't feel bad if you do too. I mean, this is pretty hard stuff. But okay. So I always go back to these diagrams because I can't remember it by heart. Yeah. So let's get back now to backup. We have a way to generate a tree of keys, and we want to back it up. We want to back up the seed. How do we actually back up the seed? Well, one way would be to simply, I'm gonna go back a bit to this one. We could actually do it like this, roll the dice, a random number generator to generate a seed, and then we save this seed on a paper in hex code or something like that. But again, there are problems with typos, and it's hard to write down hex code easy. That's probably error prone. So what we can do here is that we replace this arrow here, with something else. So instead of going directly from the random number generator to seed, we do something more here. So let's go back to this place. Instead of going directly from random number generator to seed, we do some intermediate steps. So suppose that we create this randomness here from the random number generator. we will now, from this, generate a so-called mnemonic phrase, which is a sequence of English words or words. And these are the words that you actually write on a piece of paper and store in a safe place. So, and they simply encode the data in the randomness. So you encode the randomness using a specific dictionary of words. And then from this 12 words here, in this case, it's 12 words, but it could be more, it could be 24 words as well. But in this example, we have 12 words because we have 128 bits of entropy here. Sorry, where were I? Yeah, we have written down this on a piece of paper and stored it in a safe place. And the next step is to actually generate the seed. So this seed generation, we'll go through that too later, but we generate the seed from these 12 words. So generate the mnemonic, and from the mnemonic, you generate the seed. And I'm showing you this this algorithm from going from the entropy to the mnemonic. We are starting with the entropy up here, and we are organizing them in sequence of 4 bits, in groups of 4 bits. Each character in this hex code is 4 bits. So we organize them into groups of 4 bits like this, and then we hash the entropy also to get a hash, and then we take the first 4 bits of this hash and add as a checksum at the end. You recognize the pattern maybe, but here we only use 4 bits for a checksum. And then we rearrange all those bits into groups of 11 bits. And as you know, 11 bits can encode 2048 different values. So if we interpret these as unsigned integers, you will get something like this, or you will get this. So and then these numbers are looked up in a word list that contains 2048 words, and this list is standardized. So you can use any implementation of a wallet, more or less, and read in your backups should be interoperable between the different wallets. So that's why we have a very specific word list here. So next step is looking up those words in the word list. So 471 is looked up to be depend, like this. And then you have, so you look up all those numbers, and then you will have this mnemonic phrase down here, which you then write on a piece of paper and store away in a safe place. Yeah, so this is just an illustration of that. You write the words on a piece of paper and store it in a safe. We're going to look at the next, the other box here, real quick. We're going to generate a seed from the mnemonic phrase in order to be able to recreate the full tree of private keys. So you have the mnemonic phrase up here, and you have 2048 steps of HMAC SHA-512. And it's a bit hairy to know where to break this up, but let's look at one step in this process. Each step takes the output from the previous HMAC hash function, and as key, it will take the mnemonic phrase. And then the output is bitwise XORed together with a bitwise XOR from the previous step. And you do this over and over, 2048 steps, and the last XOR here will result in your seed. This is called password-based key derivation function 2, PBKDF2. Really horrible, abbreviation, but that's the way it is. And this is something called key stretching, actually, to make it slower to make guesses. So yeah, so we use all these steps just to make guessing harder. Each guessing should take a little longer than just a simple hash or something like that. I think it's called key stretching. Okay, now suppose that the horrible thing happens, that you drop your phone in the ocean. What do? So you would probably get your hands on another phone. Maybe you buy a new one, or you use an old phone or something like that. And you install this wallet app on the phone, and then you say to the app that, hey, I want to restore my wallet. And the wallet will then ask you for this mnemonic phrase right here. So you input this mnemonic phrase into the wallet app. You take it out from the safe, read it from the paper, and input it into your wallet app. And then it does two things. First, it needs to verify the checksum to avoid typing errors. So it goes the same algorithm backwards and just compare that the checksum matches. And then it will go through the seed generation thing here with what was the name of it again? PBKDF2. PBKDF2 to get the seed. And from there on, you can just generate all the subkeys. Okay, that's neat and very useful. So we now have a way to back up once and for all, and we have a way of recreating the full tree of keys from a single seed. But there is one problem with this. Suppose that you have a web server. First of all, let's suppose that you have this master private key here, and you have two accounts, and you have a shop. You have two accounts. You have one for counter sales and one for online sales. And the one on online sales probably needs to be put on a web server so that you can create a new address for every shopping cart. So every customer gets its own unique address to pay to. That's both good for privacy, and it's also good for you to keep track of which shopping cart a certain payment belongs to, because you can look up. Yeah, you create a key, you associate a specific address with a shopping cart, and when you receive money to that address, you also know that it's the payment is for this specific shopping cart. Okay, so you want to put this extended private key on the web server so it can generate addresses for you. The problem here is that a web server is an inherently insecure environment, and putting private key materials on online computers like this is probably a bad practice, especially if you are a business with significant funds. So putting private key on the web server is not a good idea. Anyone who gets access to this extended private key will be able to regenerate all the subkeys of that private key, and thus all addresses, and can steal all the money from all those addresses. So that's not good. That's why we use something called extended public keys. An extended public key is just like an extended private key, but it only contains the public key instead of the private key. And from this extended public key, you can actually derive the same set of keys, but the same set of public key, the corresponding public keys to the private keys. So let's look at this example here. You have this master extended public key up here, which is, you take, that's a bad example, but this master extended public key can be taken directly from the master extended private key by just generating the master public key from the master private key. Okay, so you have this master extended public key. Then you can create children of this master key. You can create M0, M1, M1, M10, M11, and so on, as much as you like. And you may have noticed that I use capital M here for public keys. So this is how we differentiate when we write paths. If we write capital M/1, it means it's the extended public key at path 1. If we write lowercase m, it's the private key. Okay, so let's have a look at how we can derive a child from a master, from an extended public key.
Kalle, there was a question about the number 2048 and whether that number was chosen arbitrarily from a few slides back.
Okay, yeah, that's a good question. It is fairly arbitrary. It could just have been the double that or half of it or any number. It was just picked. I'm not sure about the exact rationale for this particular number, but it could have been anything. So you want yeah, you also want to be this. You also want this to be fairly quick for a normal user. So you don't want to wait half an hour for this process to finish. So you don't want this number too big, and you also don't want the number too small, because an attack that would make it easier for attackers. So yeah, so it's a trade-off, of course, and also this is highly dependent on technology advancements. I mean, computers get faster, and algorithms are probably getting faster too. This is not foolproof at all. I mean, but it's something. Yeah. So thanks for mentioning the question in the chat. Thank you. Okay. So now we are going to look how to derive a child extended public key from a parent extended public key. And for reference, I have put to your lower right left here, I have put the child extended private key derivation here. So you can compare them to see the differences. Okay, so we start with the parent extended public here, and we use the same hash function as we did in the private extended private, as in the private counterpart, and we also use the exact same input to this HMAC SHA 512 function. So the output of this will be the exact same as in the private counterpart. So, which also means that the write 256 bits will be the same child chain code as in the private part here. And as I said before, you can view the left 256 bits as a private key. And you can add this private key to the parent private key to get the sub-private key down here. And adding private keys has a corresponding operation on the public side. So adding two private keys also can be, you can have a special add operation for public keys that corresponds to the addition on the private side. I think they call it the group operation in crypto speak. But it's actually, adding public keys, but with a very, very special add function. So you can view this as a private key, and then from this private key you can derive the corresponding public key for that private key, and this public key is added to the parent public key, just as this private key down here is added to the parent private key. But we use a slightly different or a very different add operation here. Okay, and the result here is a public key, which is the child public key. And this public key together with a chain code forms the child extended public key. So now you have created a child extended public key from a parent extended public key without knowing the child private key, which is pretty interesting. So, and this is of course through the magic of this add operation here, public key addition. And so now we can generate the full tree of public keys as well. So let's say we use this. Let's say we want to use this extended public key stuff. Yeah. So you take this private key here for the online sales account. You take this extended private key and you derive its counterpart, its public counterpart, which is just, taking the public key for this private key and combining it with this chain code. So you have this chain code and public key. The chain code is the same as the chain code over here, but you derive the public key instead. You use the public key instead of the private key. And then you put this extended xpub on your web server. And now your web server will be able to create all addresses as needed. As new shopping carts come in, you can just create new addresses for them at will. And no private key material is ever on this server. That's good. So that's a bit safer now. But there is still one problem here. And suppose that this public extend xpub is stolen from the web server. Remember, the web server is inherently insecure. So suppose that this xpub is stolen from the web server. That in itself shouldn't be a big security issue. Of course, it's a privacy issue because they can generate all your addresses under this account. But this in itself isn't a security issue. You won't lose funds for it. But if any of these private keys in this account is stolen, suppose that M11 is stolen and this xpub is stolen, what can the attacker do then? So let's draw this picture of private key derivation, child private key derivation. So Mallory, a bad actor, has managed to get this part here, this xpub, and this private key here. Let's look at what she can do. She can, of course, having this information, she can generate this this hash here, this 512-bit hash. So she'll be able to find out these 256 bits here. So what can she do now? She has this, and she knows this, and she also knows that this is the sum of these two. So she will just subtract one from the other, modulo 2 to the power of 256. So if she subtracts this private key from this private key, she will get this private key. And now we have a whole different situation. She can calculate this, she can calculate this extended private key for the whole account. And from this, she can, of course, generate any child private keys from this. And the whole account will be stolen. Everything under this M1 will be stolen. Okay, but it doesn't end here. Suppose instead that someone manages to steal the master extended public key. I mean the public part, the public counterpart to this private key here. So someone steals the master extended public key and this private key down here. Using the same technique, she can actually steal all coins, all money in all accounts using this same technique here. So that's a bit of a problem. So you would ideally you would like to prevent this from happening altogether, but that's hard. But what you can do is that you can isolate certain accounts from each other. So you can isolate this online sales account from the counter sales account. And we do that through something called hardened derivation. And hardened derivation doesn't use the public key as input to the hash. It uses the private key instead. Okay, so let's have a look here. So you use the same hash function, and as input you have the private key and the index, and also I write it as index with an apostrophe, which means hardened derivation. So I want this as hardened derivation. Yeah, so the input is a private key here, the index, and the chain code. And this is, of course, not the same hash that you get here as you would get here in the normal child derivation. So what happens here? We take the right part and use that as the child chain code, and we take the left part and use that as a private key and add it to the parent private key, M1 hardened. So now suppose that that Mallory has this xpub here. That is not enough information for her to derive the parent private key right now, because she would need the parent private key, she would need the parent private key to generate this half hash here, and in order to subtract this stolen key. So she can't do this anymore. She can't derive the parent private key from the child private key anymore. So this is good, and a good security measure to use. So let's summarize this. So you have this hierarchical deterministic wallet, and you generate a seed like this, and from this seed you can generate a master extended private key, and from this master extended private key you can generate child extended private keys, and you can do it in a hardened way for different accounts, like this. So 1 prime means hardened, index 1. And from the account keys, you can derive child keys using normal child derivation if you want to. And those paths will look like this: M1 prime 1, for example. And from this private key, you can generate an xpub from which to generate any addresses underneath it. But more importantly, you can't go backwards up here. If you have any of the child private keys, you can't go back up to this one. You can't get to this private key here. So that's a summary of that. And this was a bit longer than previous sessions, so I hope you didn't fall asleep. And hang on a second, I will. Yeah, so you will do all the exercises from chapter 4. All right, so I'll stop recording now.